Well, good afternoon. Welcome back. I think we're like family now, so that's perfect. That means that you can ask any question anytime that you may have. The goal for today, and I think we got a lot of validation in the panel when one of the guys was asking about data protection, the other guy asking about quality of service. Our goal today is go really deeper into those two. So my name is Carrero, and I have the pleasure today to have Rakesh. He's one of our senior managers in engineering. So he's coming from Pune and coming from Madrid. Peter is coming from Oslo. So we're all together here in Netherlands. By the way, in Madrid is still summer, just to let you know. We had blue sky yesterday. So we're all coming here, and we had this goal to go deeper. It's our third conference. We got the product. We really want to explain the details to have the good understanding about how this product works. Because we're doing two things very unique together and very well integrated with OpenStack, which is quality of service and data protection. Okay? So this is going to go deeper into quality of service and how it really works, how we implement even the algorithm. Okay? So remember, the overview of HyperScale is this compute plane where we have the local storage, where we keep our first copy. There we do the read and the write cache, because we use the local SSDs or flash of the storage. And that is where we provide the quality of service. That is where our quality of service algorithms are working. The way it works is that we have that first copy, and then we do all this synchronous write. I got this question on the booth while lunch, is that all these writes are protected during 15 minutes until we take the point-in-time copy of the data plane, right? And those are synchronous writes. So you are not going to lose any write at any time. If one of those servers crashes, you get all the resiliency, which is provided to you automatically. And that's something you define in your flavors, as I showed you on the demo. So you keep that full copy on the compute plane plus the 15 minutes deltas according to your policies. What happened later is this EDS, episodic data sync, where we go to the data plane and we copy those deltas and generate a new point-in-time copy at the data plane. And this gives us the opportunity to introduce data protection, because now the data protection is done at the data plane. So today we're going to concentrate in this session now on the compute plane piece. In the other session, we will go deeper into the data plane piece. Okay, and putting all together is how HyperScale is a very unique solution for OpenStack clouds. So how do we integrate? And as I said before, when you talk to Red Hat and Canonical guys, said, hey guys, this is a co-engineering solution. So we touch different pieces within OpenStack, and you can see the contributions into open source, is that we provide a Cinder driver, which is running at the data plane, but also we have a plugin, which is running at the compute plane with Nova. So we understand what we had to place the virtual machines according to the different policies. We have a plugin for Horizon. That's where you can see, all the data management within Horizon itself. We go into Centimeter, so we understand the metrics and can provide statistics for you. So really integrated. If you take a look to the UU charms, for example, we provide 6 UU charms that you get and get automatically deployed with all the dependencies if you are using Canonical. We're doing the same thing with Red Hat and OSP Director and OOO. Okay, so really integrated, differentiated from other solutions. So when we talk about quality of service, we always talk also about predictable performance, because it is not just about cap the IOs per second. That's something that is really easy to do. You cap the IOs per second. I'm going to put a limit. Okay, it's not about that only. That helps you to avoid the noisy neighbor, because if I find a noisy neighbor, I can reduce the performance with that machine. That's perfect. But the thing is that you can define priorities. You can define different bands of performance for your different workloads. We got that question here, right, in the panel about, I have different workloads running. How do I guarantee that at least one of them or 2 of them or 3 of them get the performance that they need, right? So that's something you get. Something critical is the locality of the data, okay? And we have been experiencing this ourselves during the last week. So here at engineering, we got these results last week on performance. Last week, we released the 1.1 version. So we got new numbers versus Ceph, which is, let's say, the standard software-defined storage, de facto standard, right? And we feel the pain about adding more nodes, more OSDs, and then rebalance and everything going around and so on. And the guys from engineering told me very clearly is that, hey, Carlos, with HyperScale, when you add another compute, it's just another compute. And the storage is going to be local, plus the deltas, and the point-in-time copy of the data plane. And then when you make a read, that read is local. It doesn't have to go around the wire. So that's a huge benefit. As I said, we extend with the flavors. So it is not that you have to go to your storage array, find the volume, and then set the properties for that volume. No, you do that with the APIs from OpenStack, or you go to the UI. And you go to your flavor and define the properties for the flavor. Storage is a commodity, right? So yeah, it's a volume, but it's something you manage there. And then with this caching, that because we use the SSDs at the compute plane, so we guarantee that the writes get a low latency, okay? And also the reads are as faster as possible. So I'm going to give you one example. This is a real scenario where we define 3 types, let's say, of workloads, okay? First can be, think about the database, where I define a minimum of 10K IOs per second and a maximum of 20K IOs per second, okay? Then I run that workload for a while. Later, I run an application server or whatever that is going to have a different one between 5K IOs per second and 10K IOs per second, okay? What I do later is start running what I call noisy neighbors, okay? Can be whatever you want. What's happening is that those ones are start to get resources from the other ones, correct? But if you take a look, there is an impact of the noisy neighbors, but up to the limit of the 10K. So your database is going to get 10K IOs per second all the time, because that is what you have defined in the policy, and hopefully you will understand from Rakesh at the end how that really works, how the credits works, and how we make that possible within the algorithm. So the key thing is that, yeah, you can have noisy neighbors, but you guarantee a minimum IOs per second. Of course, at the same time, you can limit that. You can identify the workloads which are noisy. You can use the Horizon UI, make a right-click, and say, hey, you only get 1K IOs per second. That's all. And that's what's happening here. At that point in time, I get more bandwidth for my other instances, because I have eliminated the noisy neighbor. And I can change SLAs on live and say, now you get 25K, you get 15K. So you take numbers. This is an 8-node cluster. So this is the same workload running in each of the nodes. Each of the nodes is giving us 60K IOs per second. So now multiply 60K IOs per second by 8. And this is the performance of your cluster. This is where HyperScale really shines, right? It's getting IOs per second. So we switch the conversations talking about bandwidth in typical workloads to talking about IOs per second, talking about low latency, right? So we're talking about microseconds latencies here. And it's clear because it's coming from the local one, right? So with that, I did my part. Let's go to the intelligent people here. And you go out through a demo about this max IOs per second, how it works.
Yeah, thank you, Carlos. Yeah, so as Carlos said, so I'm going to start with this demo, wherein what I'm going to do is I'm going to demonstrate the maximum IOPS feature which we have in HyperScale. So we will have 2 instances running. Both, we will see that how they are performing in the OpenStack environment. We are going to limit the maximum IOP of one of the workload and see that how it impacts. OK, so here we have these 2 instances, BR1 and BR3. Both are running on the same compute. That's why I'm showing these 2. Now we will go and see that both these instances are using their respective volumes, right? Now, these volumes are running with this particular VM and getting some performance. So we have this overview tab in HyperScale which shows how many IOPS you are getting. So at the compute level, currently you are getting about 49K IOPS. You can see this IOP number for a particular given workload. So this workload is getting around 25K. And when you look at the BR1 workload, that is also getting around 24K, 25K. So the workload, the IOPS are getting distributed evenly. What we will go and put a limit on one of the workload. So you just go into the horizon, select the volume which you want to limit, say update metadata, and as we demonstrated that everything is policy driven. So you go and change the policy. So in the policy you get both maximum IOPS and min IOPS. Here I'm going to limit the maximum IOPS from 50,000 to 15,000, right? So I've limited the capacity. Now if I go and see that how this change has impacted the performance, I'll go to the same view in overview pane, I'll look at that, okay, what is the capacity which I'm getting? It's about the same. I'll jump into the workload. And as soon as I jump into I say that, okay, now this particular VM is capped to 15K. And what happens to the residual capacity which was available on the system? That is given to the other VM, which was running alongside. So this is how we make sure that, okay, you can specify a policy for maximum IOPS, min IOPS. So there is a min IOPS as well feature, but I don't have a demo for that. So you can specify policy, and based on that policy, whatever capacity is available on the system, it gets distributed amongst various VMs we have. So before jumping into the technical details, I wanted to talk about some terminologies which I'm going to use. So most of the things are self-explanatory. Capacity is nothing but how many IOPS a particular compute can serve for the VMs which are running on that particular node. The capacity is decided by the device type. You're using NVMe SSD, you're using 15K RPM disks or 10K RPM disk, you're using SATA SSDs. The main input for their calculating the capacity is latency. So we have certain latency limit that, okay, this is the latency which this storage is giving. Based on that, we calculate the capacity. The another thing which I'm continue to use is demand. Demand is nothing but the application requirement. So the application, so let's say if you have a Windows virtual machine, and in that you are running SQL Server workload. So what is that workload demanding? How many IOPS it is demanding? What kind of IO patterns it is doing, right? What is the randomness? What is the parallelism of that particular IO? And what is the IO size? So in HyperScale, by default, we use 8K IO size, but application can vary on. Some application will use 4K IO size, some application will use 16K IO size. So based on that, we calculate the respective demand. Then we have policies which we discussed about, min IOPS, maximum IOPS, and that deserves that identifies how many credit this particular virtual machine is going to get from the available capacity which we have on the compute. So this is what we tell credit. And the other and the most important feature which we have is QoS priority. Administrator can define priority of a flavor at the flavor level, which means you can specify or segregate which workloads in your environment are higher priority than the others. We are going to see a live demo for this one. But before that, I'll tell you the architecture detail in terms of components. So when we talk about quality of service, we have 3 major components sitting inside the storage stack. So as Carlos earlier mentioned, that okay, we have our storage piece sitting on both the sides, with Nova on compute plane and with Cinder on the data plane. So on Nova, we have IO scheduler. In this IO scheduler, we basically have 2 IO scheduler which we name them as L1 and L2. L1 scheduler sits closely with the application and monitors how much or how many IO this virtual machine is allowed to push down the stack, right? L2 scheduler sits near the storage, wherein it understands the storage, see that, okay, what is the queue depth of the storage which this storage can service, plus what is the latency which we are getting. And it, before putting, flushing down all the IOs to the storage, it sequences the IOs based on the deadline. So that's what the L2 scheduler job. We have another component called QoS controller. This QoS controller takes all the load of calculating this capacity, allocating the available capacity to different virtual machines which are running in the environment. Right? And the third component which we have is monitor. So if we think on it, right? So when application is doing I/O, and we need to decide that, okay, this I/O should go through the storage or not go through the storage based on the priority or based on the whatever creditors are allocated to it. We cannot have all the calculations done in the I/O code path. Otherwise, we'll have the huge I/O latency for the application. So what do we have is, okay, so I'll talk about this one, so how it happens. So let's say I'm going to take an example over here is that in this example, we have 3 virtual machines running in a single compute. From our QoS controller, we have got that, okay, this system can service about 100 IOPS in a given second. And based on the application demand, based on the QoS policies which administrator has specified, QoS controller has distributed the capacity. So the VM1 is getting 20, VM2 is getting 30, and VM3 is getting 50. Now, how scheduling works? So as soon as an IO is taken, so each IO will get tagged based on the credit and deadline. So let's say VM1 is doing 1 IO, it is pushing 1 IO. We tag the IO saying that this is the first IO of the 20 which are allowed. It does the second IO, we tag that IO, they're saying that, okay, this is the second IO. And as soon as we learn that, okay, application is doing more I/O than what it is allowed, we automatically schedule that I/O for the next second. So this is how we control the I/Os in our storage stack. So this is how we will get every I/O to our scheduler. Once we know that, okay, what all I/Os needs to go to the storage stack for this particular second, we go to, before putting them down to the storage, we sequence all these I/Os by using a simple virtual clock algorithm, which will put the I/Os in a sequence based on their I/O sizes. And then we sort these I/Os based on the deadlines, that, okay, which I/O needs to go first on the storage, and then we push them to the storage. So this is how the scheduler works in behind the scene on Nova Compute. Credit distribution. So this is another complex piece wherein we decide from the available capacity, how do we know this VM is allowed to do so many IOPS, right? So let's take an example that I have a system, or I have a Nova Compute which has a capacity of 300, means 300 IOPS are allowed. I have 3 virtual machines running on this compute, VM1, VM2, VM3. All these 3 have their own policies defined by using their flavors, or if administrator have changed some of the properties during runtime. So let's take an example of VM1. VM1 has a demand of 400. It means the workload running inside the virtual machine can ask for 400 IOPS per second. So that's the heavy workload which is running. From the priority perspective, it is defined as 1 in its flavor. Minimum IOPS are defined as 20. Maximum IOPS are defined as 50. So similarly, the rest of the properties are defined. I'll go one by one, but let's see. So QoS controller, first thing what it does is like it assigns the minimum IOPS to all the VMs, because that is what we have to guarantee when we are sitting in the storage stack, that every VM which is running on the compute, if the capacity is available, they get their minimum IOPS. So first, every VM is going to get 20 IOPS. Now the second is like, okay, what is the remaining capacity after allocating the minimum IOPS? So we take out 60 from the available 300, we got 240 IOPS. Now the next credit distribution happens based on the priority. And it is, again, it looks like a simple formula, but we'll see. So how do we divide is whatever is the capacity is available multiplied by the priority of that particular VM divided by the total capacity, total priority on that, of all the VMs running on that compute. So it's like kind of percentage. So if my priority is 15%, I'll get 15% of the share. My priority is 50%, I'll get 50% of the share. So if we take an example of VM1, VM1 priority is 2. And collective priority of all those VMs which are running on this compute is 2 plus 3 plus 5, which is 10. So the simple formula, remaining capacity 240 multiplied by 2 divided by 10, 48. So this VM gets additional 48K IOPS because of its priority. Similarly, next VM gets 72 additional because its priority is 3. Third VM gets 120 additional, which is 240. Now, what we have to do is like we need to see that, okay, we have taken care of demand, we have taken care of priority, we have taken care of min IOPS, but there are other 2 things which we need to take care of, which is the maximum IOPS, plus are we going beyond or are we wasting any IOPS? So we'll see. So what we do is like, once we have distributed all the capacity on the system, we will readjust the IOP allocation. So for VM1, we see that, okay, this VM has got 68 IOPS capacity for this particular second, means this VM can do 68 IOPS. But as per policy, this should not do more than 50. So what we are going to do, we are going to take out additional 18 IOPS from this one. In the next case, what we see that, okay, yes, this VM has the max IOP. From the policy, it can get it. But the workload which is running inside the VM is not itself requiring those many IOPS to be done, right? So even if we allocate that capacity, those are going to get vested for that particular second. It might generate that demand later on, but right now it is not needing it. And if somebody else needs this capacity, we can distribute this. So we'll take out the additional 12 credit from this one, and whatever residual capacity is there, we give it to the third VM. Right? So this is how. So and all this calculation happens every second, based on various parameters which we discussed earlier in terms of what is the storage throughput I am getting from the storage stack, what is the application demand I am getting, how much time I am taking to complete a particular I/O. Okay, so this is the QoS priority demo I am going to run into. And in this demo, what I'm going to show is like I have 2 virtual machines running with the same flavor, and the priority of that flavor is 1, I'm going to show. So with the system capacity of 50 IOPS. So both these VMs will share the available bandwidth. what I'm going to do is like I'm going to instantiate one more VM with the same flavor. We will see that, okay, all 3 VMs will start sharing the available capacity. Then I will create a new flavor and see that, okay, how it makes a difference. So with that, I'll jump into the demo. So these are the 2 VMs which I have running on my machine. And both these VM are using the same flavor. We'll go and see what this flavor defines. So you go and say update metadata, where you will see all the QoS flavors. In this QoS flavor, we are seeing that, okay, it has a maximum IOP capacity, minimum IOPS, and QoS priority. Currently, QoS priority is set to 1, right? Now what we will do is like we will go and check that, okay, what is the IO performance we are getting for both these virtual machines. So similar, we'll go to the HyperScale tab, overview, where we can see the details of a virtual machine. So the total capacity on the system is 52. If we look down to the workload view, wherein first VM is getting about 26K, if you look at the second VM which we have on the machine, it is also getting about 27, 28K. So both the VMs are kind of equally sharing the limit. What we will do now is go and instantiate another VM. So we will go to the project, instances, right? We will just launch an instance. In launch instance, we'll specify the VM name, what VM name we want to have. We'll specify the volume through which we want to create. And once the VM is created, we will go and see that, okay, what is the performance it is getting. So earlier, there were 2 VMs sharing the capacity. Now we have 3 VMs which will share the capacity. And all 3 VMs are going to get the same capacity, which is about 13K, or sorry, 18K in this matter. So first VM is getting 18, second is also getting about 18K, and the third VM is also getting about 18K. Now what we are going to do is, we will go and create a new flavor. And while creating this new flavor, we will, and this new flavor will have higher QoS priority. So first, basic attributes of the flavor, we are naming it a performance flavor. We'll specify rest of the attributes, like what is the RAM of, should be, what is the vCPU usage, and just done with it. When the flavor is created, we will add HyperScale specific metadata to this particular flavor. So we have HyperScale flavors. Once you add this flavor metadata to the flavor, you get reflection factor of the compute, you get maximum IOPS property, you get minimum IOPS property, you get data node reflection flavor, and you also get priority. So QoS priority can be defined from 1 to 4. 1 means the lowest, 4 means the highest, right? So for this demo, we are going to create a flavor with QoS priority 2. What we will do is, once the flavor is there, we will launch an instance with the newly created flavor. So we'll go to the instance tab, just say launch instance, specify the instance name. So for differentiation, we'll add the performance to it. So let's say we call it BR4 performance. We'll select the source, which is a volume. We'll select a volume. Now when we are selecting the flavor, we'll select the performance flavor which we have just created with the QoS priority 2, right? And we select all other necessary properties like network, launch the instance. Once the instance is launched, spawn an inactive state. We'll see, go to the HyperScale tab and see that, okay, how much IOPS it is getting. So yeah, so the newly created instance is getting 20K IOPS, 28K around, and rest of the 3 VMs which were running earlier, all are now getting 13K IOPS because their priority is 1, and this performance instance which we have created with the QoS priority 2. So this particular performance instance is getting double IOPS of all the rest of the VMs. So yeah, this is what I had to kind of cover in this demo. Questions? We can take any questions if there are.
Yeah, so I think one of the key things, this is my understanding from more higher level. I don't know if this was too technical, guys, maybe, but I think it's a lot of value here to understand is that this is a really holistic view of what's happening on the application, of what's happening at the spindle level. Okay, making sure that you get all these parameters and give them a good message, and then assign the priorities to each of them. So yeah, thank you.
Yeah.
Any questions that you may have?
So it's maybe slightly off topic, but it's directly linked to this. What if so it's very modern to have like VMs in OpenStack and have something like Kubernetes, Docker inside of it, so you get 2 layers. How do you deal two places where the top of the I/O, because you have the L1,
Yeah.
where you have the L2 scheduler. How do you do that?
Correct. So I'll take this question. So as of now, we are only taking care of the virtual machine level. So you have an OpenStack Nova compute, and in that you have 5 instances running. So we really don't go and see that, okay, if there are any containers running inside those virtual machines. So we do have a HyperScale product only for containers. So see, it's not a simple storage product like any other which we have in the market, right? We tightly integrate with OpenStack, wherein to take an example, flavor, right? So flavor is an OpenStack construct. We want administrator to go and specify your QoS requirement in the flavor itself. So this solution, when you want to work with this solution, OpenStack, it works at the virtual machine level. You can go and, so if a virtual machine has 5 volumes, then you can specify that, okay, this volume's QoS properties are different than the other volume, though both volumes are attached to the same VM. But if you want to use for the containers which are running inside the VM, then you have to use another product, which is HyperScale for containers, which actually talks about the containers, and you can control these QoS parameters at the containers level. Sorry?
Can you layer them? Can you stack them on top of each other? You get this double scheduling problem.
Yeah, right now, no. So the product which we have released for containers last week, right now, it is not possible, but yes.
HyperScale for containers is the same value propositions for OpenStack, but really allows you to run containers on a bare metal. So it's about reducing that number of layers. It's getting that persistent storage with all the quality of service. The difference is that here with OpenStack, you have the flavors, right? What we do is that with HyperScale for containers, we have a different UI, a beautiful one, where you can define your SLAs. And then when you create a container and you have to attach a volume, you just tell that volume what is the SLA for that volume. So the same stuff, the credits, the quality of service, you can get that for containers and Kubernetes today, running on bare metal and having HyperScale to manage all of the storage for you. Really simple. That's a good question.
How is the capacity, your creative capacity?
Capacity on?
Yeah, your creative capacity, how is it defined, the capacity per host, I guess, or per storage system in the backend?
Yeah, so it's not the storage system in the backend, it's the actual devices. Storage device define the capacity. So storage device has multiple property, right? So when you buy any storage, let's say you're buying NVMe SSD or you're buying an SSD, it comes with a specification that, okay, this SSD has this much of the latency, and this can service these many IOPS in a given second for this IO size, right? So since we have the history, since we at the L1 level, we know that, okay, how many IOPS application have pushed into the storage stack. We monitor the time taken for that particular IO. We do this for every IO. We do this at 2 levels. That, okay, once at the application level and once at the storage level, which is done by the L2 scheduler. So on the past second, we have monitored everything. We use the data to calculate the capacity for the next second. Right? So it's not that, okay, it's at the static level, once you have configured the system, it is done and dusted. So that capacity gets revised, recalculated at every second and used for the next stick. Similarly, it goes for demand as well. Even in the demand, it might happen that a SQL server running for this instance probably pushing too much data, but later on it might reduce the its IO operation. So that is where it generates the less demand and will give the less credit. Yeah, so that is where I said, right? So we do not sit in the IO code path. That is where we have the controller and the monitor piece separated out from the IO path. So we have a separate component running on the Nova compute node, which does not interact or come in between the storage stack. So when application is doing IO, what it is doing, it is just checking the tag that, okay, I have 20 IOPS available, and there is a counter which says that, okay, 1 pass, 2 pass, 3 pass. Okay, 20. Now you don't allow, Mr. IO, you are not allowed to go anymore. You are scheduled for the next tick. No overhead in the calculation IO path. There is a separate thread who are doing the IO calculation. So you don't get a load on your IO code path.
Great. Well, thank you guys. We're running out of time. Yeah. So we're going to be on the booth to keep talking to you, any other questions you may have. Thank you very much, and have a good day.
Thank you, guys.